All right. If anybody wasn't here on Wednesday and needs a syllabus, I've got some copies up here. If you weren't here, just note that I am videotaping every class, and you can get onto Moodle and you can see Wednesday's class on videotape. So if you missed it, there's your opportunity. Any questions from last class? That's the first order of business. Anybody had any questions about the syllabus or what's going on? Yes?
So the book we can find online, the main textbook, and then you had two other recommendations for books, which...
No, it's all the same book. If you're happy with PDF copies to read online, you can get it free through the library. Mm-hmm. If you want a print copy, you can get a $25 paperback through the library. And if you want a good hardback to keep for the rest of your life, which is nice, you can go to the bookstore, to Amazon. You can pay about $100 or something on that order, and get a copy. But there's only one book that's required for the class.
Okay.
All right. And it is this. Okay. All right. Another item I wanted to mention is that my office hours are right after class. However, sometimes things get scheduled and I have to unavoidably adjust things, and today's one of those days. I'll be available right after class today to talk to students. I have a meeting that's supposed to start at 9:30. I'll go there late, but if everybody's done talking to me and it's 9:30, I'm probably going to leave. So if you decide to go off and come back at 9:45 to try to catch me at the end of my office hours, you may find my office empty. So if you want to talk to me after class today, meet me right after class. All right. Today we're going to talk about biomechanics and whole body biomechanics, kind of things that exercise scientists study. And we're going to start off by talking about when I was back in high school. And sometimes our PE class would get out the gymnastics equipment, and we'd all do gymnastics. And I was really bad at gymnastics. And one of the things they do is they had the rings, and the rings would hang down from the ceiling. And the only thing I could do on the rings is I could reach up and I could hold the rings, I could swing back and forth. I couldn't do any of the other tricks. So I always had not so good grades in PE. But the real pros in gymnastics can do this thing with the rings where they're hanging and they're holding their arms out like this in an iron cross. And of course their feet aren't on the ground, they're suspended in air like this. So it's an amazing amazing feat for any gymnast. Anybody done gymnastics and done the iron cross? It doesn't surprise me. It looks like it'd be extraordinarily hard to do. Well, one thing I want to do first of all today is to look at the iron cross and try to figure out why it's so difficult. So we'll begin by something really simple. We'll just look at your whole body. If you look at the whole body, you can kind of make a simple model. Here's the person. Here's their arm sticking out, and their hand is holding the ring. And then there's the body hanging down like this. And this is a really simple case because we're going to be doing today statics. That is, there's no net motion. The object's stationary. And if there's object stationary, then Newton's second law, F equals ma, just becomes sum of the forces is equal to 0. So when you do statics, this person has a weight, W, and that weight has to be supported. He's not accelerating downward. That weight has to be supported by these rings. So that means each hand is being pulled up by the ring. And if you assume it's symmetrical, which usually it would be, each hand is supporting W over 2 of the weight, so half the weight. So that's a really simple picture of the whole body. But in order to get some really deeper understanding of what's going on, we want to make a mathematical model of the arm and the muscles on the arm and try to understand what's really happening in a little more detail. So this is going to be our first example of a model. One thing that you can almost call this whole class as mathematical modeling applied to physics, applied to medicine and biology, because we're going to be building model after model. Each one of these models is sort of a simplification, but we try to include enough to get really the essence of the problem. So here's the model we're going to use. We're going to assume the arm is a stick with a hinge. So we're going to completely ignore the elbow and just think of it as an arm with a hinge. So out here at the end, you're hanging on with your hand to the ring. So there's going to be a force which is going up. W/2, that's that force. Now, this little hinge here, that represents the shoulder. So your arm is hinged around the shoulder. So your shoulder can exert also a force back on your arm. That's kind of like a normal force. Kind of like I'm standing here on the floor and the floor is pushing back on me and that's why I'm not falling. Well, your shoulder is going to exert a force on the arm. And I'm not quite sure what direction that force is going to go. I'm going to call it R. I'm going to draw it this way. Now the good news is if I draw it in the wrong direction, I'll just end up getting a minus sign in my solution, and that minus sign says, oops, I did it in the wrong direction. So we don't have to worry too much about the direction that we draw that force. And there's going to be a third force, and that is because there's a muscle involved. And the muscle is the key because that's the muscle that was never strong enough for me to ever do anything like this. And it's a muscle that goes right here. It basically connects your chest to your arm. It's called the pectoral muscle. It's the one that gives, when guys work out, they have the big, strong, bulky chest. That's this pectoral muscle. So we're going to say it's going to be attached to the arm here, and it's going to come down and exert a force T. Now we need to know a little more geometry. We're going to assume that this is a 15-degree angle between the arm and where that muscle attaches. Again, this is a model. It's actually more complicated. Where the muscle attaches is probably spread out over some distance. The angle is probably not constant. But we're going to assume it's that. And now we need a couple more pieces of information. The length of the arm. Well, how long is an arm? Not too different than, it's a little shorter in the meter. We're going to give it 50 centimeters, which is half a meter. Which might even be a little on the short side, but we're back talking about when I was in high school, so it's kind of a shortish arm. And this distance here is much shorter, 5 centimeters. 5 centimeters is about like that, and that's how far the pectoral muscle is attached up onto the arm. So it doesn't go too far. Your muscle's not attached out here because we don't have a big muscle here. All right, so that's our picture. Now, the next thing we want to do is we need to get axes. We're going to have to do forces are vectors, so we need to get components of the vector, so we need to get components on a certain axis. This one's really simple. It's pretty clear that we want to do horizontal and vertical. So if that's an option, it's usually a good option. I'm going to take horizontal to be x to the right, and y is going to be, did I take it up or down in my notes? I took it up. Okay, y up is the other axis. Okay, so you're in static equilibrium. So the first condition is, the condition is going to be sum of the forces is 0. So let's first do the x components. What we want to do is we want to find all the forces that are in the x direction, and we want to add them up to 0. So sum of fx equal to 0. So really it's like studying a bridge or some object you're just sitting there. So what forces are in the x direction? Anybody see a force in the x direction?
R and T,
R has a component in T. Let's do T first. T is pointing over towards the left. So its x component is going to have a minus sign because it's pointing in the x. And then you have components of a vector. I assume if it's introductory physics, you're familiar with taking components of a vector, but if you want the component along the x-axis, you would get T, and then you had cosine of 15. There is an appendix in the textbook that talks about components of vectors if it's been a while since you've had introductory physics. And now, R is a little trickier because I didn't tell you what the angle is because we don't know it. So what we're going to do is we're going to take R and we're going to decompose it into an x component and a y component. So just going to write its components like that. So we got two unknowns. its x and y components. It's kind of like saying we have two unknowns, its magnitude and its direction. Okay. So Rx, going the way I've drawn it more or less in the positive direction, plus Rx. And this is not in the x direction at all. So what we've got is an equation. We really have three unknowns here. We have Rx, Ry, and t. We don't know t. We know its direction, but we don't know its magnitude. So we got two of the unknowns here. So what do you do next? What are you going to have to do next? We only have one equation. We have two unknowns, so we can't solve this yet.
Sum of y.
Some of the y's. Okay, so let's do the same thing in the y direction, because it's not accelerating downward. So we will get, what do we have in the y direction? Well, now we have this force coming in, W over 2. And we also have a y component for the t, the force of the pectoral muscle. And that's going to be more or less downward or negative. And what's that going to be? T sine theta. T sine of the angle 15. And finally we have r, and r is a y component, and it's going downward, so it'll be minus ry equal to 0. Okay, so now we have two equations, but we have three unknowns, so we're still short an equation. So what do we do next? Who's had that remembers their introductory physics? What do we do next?
We do the torque.
The torque. So what's a torque? A torque is a rotational motion. We assume that not only are we not moving in the x and y direction, but we're not rotating either. And torque is a force times the distance. And the idea, let me show you with the door, it's a lot easier for me to open the door if I push on it out here, because it's a long moment arm, so I can have a small force and still have a big torque to open the door. If I try to push on it here, I gotta push, because that moment arm is so small that I need a huge force to get the same torque. So torques are force times the distance. So let us apply, and sometimes the torque is given the symbol tau, Greek letter tau, and those are going to have to add up to 0. In 3 dimensions, this gets a little more complicated, because then you got to figure out the torques in 3 dimensions. You're asking what direction is this, but in 2D, it's just going to correspond to a rotational motion. And just as we said, x is to the right and y is up, we have to give what is our positive motion for torque, and that means we have to look at rotations. And here's another thing, is that you can take the torque or the rotation about any point you want, and you always get the same answer. So you got a lot of freedom. But usually in a biomechanics problem, there's a natural place to take the torque, and in the iron cross, the natural place is right here at the shoulder, because that's where the joint are you're rotating. So we're going to take the torque about this point, and I'm going to call this counterclockwise motion, this the positive motion. It's not too important whether you take clockwise or counterclockwise as positive, as long as you do it consistently for all your forces. If you start getting inconsistent within the problem, then you'll get some sign errors. Okay, so here is the torques. Who could tell me what the torque is corresponding to this force? Corresponding to the force of the rings on your hand.
W.
Yeah.
It's 50 centimeters in length.
Okay.
The arm, the distance from the shoulder to the ring.
Okay, 50.
And then you also have multiplied that by the weight divided by 2.
W over 2. Now, is this going to be a positive or negative? The way I do think about it is, okay, so if this is pulling up, so if you actually did this and you started pulling up, which way would you rotate? You're rotating like this, which by my convention would be minus. Now, you might say, oh, do I have to convert this to meters? Or can I leave it in centimeters? Well, we're going to see that the moment arm, always sort of units of it will cancel out, and you'll see that here in a few minutes. So it doesn't really matter whether you use centimeters or meters or anything else. But, so for the moment, we can get away with just writing this as 50 times W over 2. All right, so that's the torque from this one. Now, let me ask, what's the torque for vector R? 0, because there is no moment arm. Basically, vector R acts through that joint. So even though the force may be very large, it has no torque. It's kind of like, right, if I push right at the hinge of that door, doesn't matter how hard I push, I'm not going to rotate that door. You're going to have 0 torque. So one reason why we take this point, besides this sort of the biologically natural point, is we take this point to be our center of rotation because it gets rid of Rx and Ry. Both of them go straight through that point, and that means neither will contribute to the torque. But there's still one thing left contributing to torque, and this is the trickiest one of all. That is this force. And now you have to ask yourself, what is the torque produced by this force? And so, first of all, if you pulled on this, it would tend to rotate the whole thing like this, and that would be in the positive direction. So we expect this is a positive. Moment arm is 5 centimeters, so we get a 5. But what's the force? Yeah.
The sign of the magnitude.
Yeah, you really want this component of t. So you want t sine theta, the same thing you had here. You think of t as having two components, one in the y direction and one in the x direction. Well, the one in the x direction goes through the point and doesn't have a moment arm. It's really the y direction force that goes through, that gives you the torque. So you're going to get t sine of 15 equal to 0. And now we have 3 equations, 3 unknowns, and we can solve this problem. So if you had this problem on an exam, probably I'd give half the credit just for setting up these 3 equations. That's the real physics. And then now solving these 3 equations is just the math. That's still important to do, but I want you to be able to set up the physics and solve the math. So here we are with our 3 equations, 3 unknowns. Yes?
I have 4 unknowns.
What would be the 4th one?
The angle of R.
We've divided R into 2 components. So once you know Rx and Ry, you can find out the magnitude and the angle given Rx and Ry. In other words, R, magnitude, is Rx squared plus Ry squared square root. And angle, I'll call it phi, is inverse tangent of Ry over Rx. So if you know Rx and Ry, you can get magnitude and angle of the vector. So whenever you're dealing with a vector, if I ask you, at least in a 2-dimensional problem, if I ask you, tell me what is R, vector R, you can either tell me 2 components, Rx and Ry, or you can tell me a magnitude and the direction. Both are essentially equivalent and would be correct.
I was thinking W wasn't given.
W, we're assuming the weight in a person's where we're going to end up solving everything in terms of W. So
Okay.
W, technically I haven't given you a number for it, but we are going to try to do things a little more abstractly. Basically, we're going to try to find all these other forces in terms of W, and then you can stick W in for any particular person. Other questions at this point? All right, so 3 equations and 3 unknowns. Anybody have a suggestion for how to begin? Because there's a particularly simple place to begin. Which, yes? You can find T in terms of W here. The nice thing about the torque equation is it only has 1 unknown. This equation has 2 unknowns, this equation has 2 unknowns, but this equation just has 1 unknown. Again, W we'll assume is known. So we just solve this for T, and we're going to get, now here you're going to get a 5 coming down in the denominator. Remember, this was 5 centimeters, this is 50 centimeters. So when you bring it down to the denominator, you'll get 10 for the ratio, 50 over 5. The centimeters will cancel. So if you had converted everything to meters, you would have had 0.5, and you would have had 0.05. And when you divide them, you still would have gotten 10 dimensional. So that's why I said you don't really have to convert to meters, because you've got the same units in every term. That works as long as it's static, so it's just equal to 0. So we're solving for t, so we brought the 5 over. We still have a w over 2, and we still have a 1 over sine of 15. Okay, so we're almost there. Let's get our calculator out. You definitely want to have calculators for your exam, and you want to make sure that you know whether you're in the degree mode or the radian mode. But let's take 10 divided by 2 and divided by 15 degrees sine of 15 degrees, which is a pretty small number. And what you get is 19.3 times W. Well, this is interesting just in itself. This says that the force on the pectoral muscle is almost 20 times the weight of the person. You know, a person can be a pretty good weight, but 20 times. That's why I couldn't do the iron cross, and probably why most of you couldn't do it either, because your pectoral muscle has to support a lot more than just your weight. You have to support a huge force in order to do this this gymnastic event. Let's go ahead and solve the others while we're here. Once we have t, we can stick it into this equation. We can get Rx. Rx is equal to t times cosine of 15. Cosine of 15 is pretty close to 1. So this comes out to be 19.2. I'll leave you to actually work out the numbers. And we can solve here. Our y, bring it to the other side, is 1/2 w over 2 minus 19.3. That's big, but remember sine 15 was really small. So when you do the math, this ends up giving you ry equals minus 4.5 w. Okay, minus. What's that mean?
The opposite direction is gone.
That means the opposite direction from what I guessed. The opposite direction is gone. So really, r should have, it is correct that its x direction is this way, but its y direction should be up. So really, r could have been drawn as coming up like that. Then you would have gotten all positive numbers. It's fine just the way it is. If you clearly show me what direction you think it is and you calculate out the negative value, you're done and you get full credit. But at some point you might say to yourself, boy, I'll redo the problem and I'll draw r in the correct direction. You could do it that way and you get all positive numbers. Either way is fine as long as it's very clear what you're doing. All right, and to go back to what we said about the vectors, now that we have Rx and Ry, we can calculate this angle. And that angle comes out to be 13.2 degrees. And we can calculate the magnitude of R. This is by far bigger than this, so the magnitude of R is almost the same as Rx. It is about 19.7 times the weight. Now it's useful, even though we're done with the problem, it's sometimes useful to think about your answer and to say, what do these forces really look like? Here's your arm, here's the ring, and let's see if we can draw these forces. I'll use green for the vectors. Well, W over 2 is this little thing. And it's not little, it's half your weight. But R, we had R going in sort of the wrong direction. R is actually a great big vector like this. And T is a great big vector like this. And the reason why T and R, they're almost canceling out. They're almost exactly the opposite direction. The reason why you get this big effect is because of the moment arm. The torque equation, which had the sine 15 in there, which went in the denominator, made everything so large. So basically, it's the fact that your muscle is attached so close to your arm that in order to get the torques correct, you have to exert this huge force on the muscle. And if you have this huge force on the muscle, that's going to cause a big back force from the shoulder in order to balance things. So you get these giant forces kind of working against each other. And this is very common in a lot of biomechanics examples. We can have large forces that are almost sort of pushing against each other, acting against each other, acting in our body, and causing, making some of these like sporting events so difficult. Okay. Questions? That's a classic example of a biomechanics problem. Do you have any questions on that problem? You can do this one. Well, this next one will be a little bit harder, but not too much harder. But if you can't do this one, then you're probably going to have trouble with some of the others. You have some homework problems, which we will talk about in a minute. They're all sort of along these same lines for some of the homework problems. I think 16 and 17 are going to be biomechanics problems. Okay. Now I'm going to erase this, and we're going to do another problem. So, here we go. Now, if you look on the back of the syllabus, there is a detailed schedule, and it includes, if you have the color copy in green, homework problems to work in class. We will often have one homework problem that will be designed. It won't be on your homework assignment usually, but it will be from the book and sort of sums up the whole discussion that we're having. And today, that homework problem is going to be problem 1.10 from the book. So, let's do problem 1.10. And this one, since I pretty much did the last one, we'll do this one together. So, let's see what it says. All right. And this one, there's a story behind this one. About a couple months ago, we were moving some stuff from my parents' place in Kansas City back here to Michigan, and we had rented a nice minivan to do it, and I had to load up the van. And you know, you always hear from your mother, usually, you're supposed to lift with your legs and not with your back. Well, I had to get this big sort of a cedar chest into the van, and I lifted it wrong, and boy, I had a backache that lasted about 2 weeks. And in the first few days, it was excruciating pain. It really drove home what this problem is going to tell us. We're going to do an analysis of the forces on your back when you are lifting and try to understand what's happening. So this one has a little bit of significance for me this year, didn't have in the past. Okay, consider the forces on the spine when lifting. Okay, approximate the spinal column as a stiff bar of length L that has 3 forces acting on it. So immediately, we're making a model. And we're assuming a lot. Your spine has a lot of internal motion it can do. We're ignoring all that. And we're treating the spine as a stiff bar of length L. Okay, so that's your backbone. Now, it has 3 forces. What are the forces acting on it? Okay, first of all, W is the downward force acting at the top of the spinal column. This is coming up through your arms. You're lifting something. You're lifting a weight W. Okay, so you have a force W here, because the object weighs W and that gets transferred to your spinal column. Now, what else do we have? We have the F is applied by the erector spinae muscle, which is a muscle along your back, and that's the muscle that's going to make you do this kind of motion. It's not a real big muscle, which is one reason why you can get injured. It's about 1/3 of the way down from the top. And it's got a 12-degree angle. So 1/3 of the way from the top, this muscle comes in. Let's do our forces in green, just that way. It's a little easier to see. And it's got a 12-degree angle. We're calling it F, and that's the muscle. So the muscle attaches somewhere up towards the top of your back. It's got a real small angle because obviously there's not a muscle coming out here out of your back like this. So it kind of sneaks down along your spine. And then finally there is the pelvis. That's where the bottom of the spinal columns attached, and it has a force. And again, we don't know exactly the direction of that force, but we'll call it R. And the whole thing, we're going to be looking at this kind of motion. So the natural place to kind of take your pivots is down here at the bottom of the spine, and where the spinal column attaches to the pelvis. So that's going to be our model. And we want to be able to now look at this not only as a function of W like we did last time, but I want to look at this as a function of the angle that the spine makes with the horizontal. So that is our model. So it's very similar to the last problem. The thing that makes this more difficult is that we got the spine off at some funny angle. It's not straight up or straight across. So we have to do a little bit more geometry just to solve the thing. Okay, what are we asked to do? Determine R, F in terms of W and theta, and then a few other questions about the problem. So, what is the first thing we did last time? For the last problem. Even before we started calculating forces and setting them equal to 0. Set up a coordinate system. Last time it was obvious. This time it's not so obvious. There's two that I could think that would be good candidates. You could use horizontal and vertical again. And that'd be nice because W is perfectly vertical. But what's another option? Yeah. Oh, you could use polar, but that would make life more difficult, I'm afraid. Yeah. Did you have a suggestion? All right. You could have it going off this way. Never tried to solve the problem like that. I bet it would be more difficult too.
Odd angle is fine.
You could have basically along and across the spine. And that's in fact the coordinate system I want to use. Let me stress, you could use up and across, vertical, horizontal, and you still get ultimately the same answer. It just might be a little more difficult. Maybe it wouldn't. I'm going to take the x direction as being along the spine, like that, and my y direction as being perpendicular. If this way is going to be the positive direction. So you have to choose a coordinate system. So the one nice thing about this problem is it's not a trivial decision. But that's one we'll use, and you can try to work it out in class, maybe using a different one. What are the equations that we're going to use? Well, what was the first one? Sum of the force is 0. In particular, we'll do Fx is equal to 0. So what do we have in the x direction? Well, already it's a little bit difficult because this W, what direction is that in the x direction? Well, this is one of the reasons why this is a little bit harder coordinate system to use. However, there is an old rule from your back in high school geometry. If this direction is perpendicular to this direction, and this direction is perpendicular to this direction, then this angle here has to be theta. Now, the way I remember that is if you made this angle smaller and smaller, then this angle, as it came down, would be closer and closer to the vertical, and you'd expect theta to get smaller. If you made theta larger, so it was almost straight up, then this angle would be almost straight down, but the dotted line here would come across, so theta would be big. So that's probably one of the hardest parts about the problem, is to realize that that angle is the same as that angle, just from geometry. And in an even more complicated problem, you might have to do more gyrations of geometry to get all these angles, but we have it. So now, what is the force in the F direction from this weight?
W sine theta.
Okay, it's W sine theta, but it's more or less in this negative direction, so it's minus W sine theta. Theta is a parameter, and we don't know it, but we do know that it's a force. Okay, F. What is the force from F? Well, it's more or less negative, and it's this component of F along here. So it's an angle 12, so it's a cosine of 12. We're just resolving f into a component along and a component across. Now r is the same issue that we had last time. We don't know its direction. So we're going to do the same trick. The trick was we're going to resolve r into a component along, which would be rx, and a component perpendicular, which is ry. So rx plus ry is equal to r. And now this is pointing in the positive x direction, so you really get a plus rx equal to 0. Some of the forces. Same problem we had before. What are we really going to be solving for? Again, rx, ry, and f. We've got two of them in this equation. So, everybody with me. What's next? Some of the forces in the y direction. That would be 0. So, what's the y component of this thing?
W cosine theta.
W, actually, yes, W cosine theta, and it's positive, so you're exactly right. W cosine theta. The y component of this?
Negative sine theta.
Sine 12, because you're really looking at this y component of this one, and it's pointing more or less in the y direction. And what else now? We need one more. What is ry? Ry is a plus. Ry equal to 0. All right. Well, we still have 2 equations and 3 unknowns, so we got one more thing to do. We have our torque. Sum of the torque equal to 0. We're going to take torques about this point, and once again, I will take clockwise as positive. All right. So, here's an easy question. What is the torque from force R? 0. That's one of the reasons why we chose this point, is because that means both Rx and Ry go back directly through that point so that it has no contribution to the torque. What is the torque from the erector spinae muscle in the back?
F sine 12 cross 2/3 L.
So it's negative, and it's F times sine of 12, because that's this component here. And now, what did you say for the moment arm?
2/3 L.
Okay, that's a little tricky. Yeah, but it's basically that. It said it was 1/3, so let's call the whole distance L. We weren't really given that. But, so we better hope that the problem doesn't depend on L, because we weren't told how big L was. But we were told that this distance was 1/3 down, so that's L over 3 down to here, which means that this distance here is 2/3 L. And that is, in fact, the moment arm. So this has a 2/3 L, and we now have a fourth unknown, but we're hoping that it's going to somehow go away. And now, how about this vector? What does it contribute to the torque?
W cosine theta cross L.
Okay, W cosine theta would be this component. It's going to be plus W cosine theta. That's W should be. And times L, which is the whole moment arm. And all that equals to 0. All right, we have our 3 equations, 3 unknowns. We're halfway there, and all the physics is done. So only the hard part's done. Now, let's do the same thing we did before. Let's use this equation, which really has only one unknown, f, because we're assuming w and theta are our parameters. They're what we're going to solve things in terms of. So here's the good news. You solve this for f. This term has an L, and this term has an L. You divide by L, and the L's go away. So we didn't have to know L. All we had to know is that this was 1/3 of this was enough. The actual values of L didn't matter. So we can solve this, and we get F is equal to W cosine theta, this minus sign goes away when we move it over, and we're going to get a 2/3, and we're going to get a sine of 12. And if you do that calculation, this becomes 7.2 W cosine theta.
Should it be 3/2?
Did I mess it up? I did, because you're solving it, so you bring it over, and it's 3/2. Thank you. It's always brownie points to when someone catches me making an error. All right, so we get the same kind of story. The muscle force is over 7 times the weight, depending on what the theta is. So there's big forces can develop in your back, and this is why I banged up my back muscle and somehow injured it, because it had these big forces. You can go ahead and get our x and our y. I'm going to sort of leave that for you guys to do, but I'll write down what the answer is. You're going to get 7.0 times cosine theta plus sine theta. So a complicated expression times w for our x, which you get from up here because you already know f. And for our y, you can solve it. You know f, so you can solve for our y and 0.5 w cosine theta. So technically, this is the answer. And that's sort of where you might think you're going to end. But one of the mantras that we're going to have in this class is I want you to think. Think about what you calculate. I want you to think before you calculate, and I want you to think after you calculate. So if you want to really understand what this means, with all these thetas in here, the only way to really do it is to look at some special cases. So let's look at 2 special cases. Let's look at when you're standing up and you're basically have your back upright, so that's lifting with your legs because you have to bend your legs to lift something. And then let's look at the worst case scenario where you're lifting like this, completely with your back and your legs aren't doing anything. And that would be theta is equal to 90 in that case. Or so actually, I got that wrong. I define theta like this. This is theta 0, and this is theta 90. Okay, so let us look at those cases. First, let's do theta equal to 90. 90 degrees. So, straight up, we're lifting like this. What is cosine of 90? 1. So F is, how do I get this right here? Oh yeah, cosine of 90. What's cosine of 90? I screwed up. Cosine of 90 is 0. Cosine of 0 is 1. Cosine of 90 is 0. So that kills this, and you just get 0. So your erector spinae muscle isn't doing anything when you lift with your legs and not your back. Your back, your spinal column, just acts like a pillar. So Rx is equal to, well, let's see, 90, that kills off this one, and that just leaves you sine of 90, which is 1. So that just leaves you W, and your Ry, which has the cosine of 90 or 0, is 0. So what you have now is you have basically a force of the pelvis onto the bottom of the spinal cord equal to the weight you're lifting, and there is also this force at the top, which is this force, which is going straight down now. So your spinal cord looks just like that. It's just a bar under compression. But there's no forces on the muscles. There's no forces going perpendicular to the spine. And the forces are relatively small. They're equal to the weight of the object you're lifting. It's always good to remember these are models so that everything's not included. And one thing that we aren't including is the actual weight of the body, because you're lifting part of the weight of your body as well as the weight you're lifting. We're sort of assuming that the weight you're lifting is big enough that we can ignore the weight of the body itself. Sometimes that's not true. Certainly if I was just looking at didn't have any weights, but I was just doing this exercise, I'd have to include the weight of the body to make any sense. But if I had some big weights in my hands, and you're doing this, which is what's that, kind of a deadlift or something, you might have to, you could maybe ignore the weight of your upper torso compared to the 500 pound barbell that you're lifting or whatever, depending on what kind of weightlifter you are. So we're ignoring the weight of the body itself. All right, so lift this way. Now, what happens if you lift 0 degrees? So you're lifting like this. Well, cosine of 0 is 1, so you get the force is now the full 7.2 W. Our x is 0, that term goes away, and now you have a 7.2 W. And Ry is no longer 0, it's 0.5 W. So what you have is something that looks like this, where you have a little force out here, or a W, but then you have your Rx and your Ry, they're both positive, so we had the direction right. You have one of these situations again, where you have great big forces in the muscle and then on the spine, and they're acting against each other in order to make the torques work out. It's not quite as bad as the previous example because the erector spinae muscle is quite a ways up here, 2/3 of the way up. So even though this angle is small, you still get a fairly decent torque. So it's not 19, but it's still, mainly because of this sine of 12 degrees, a fairly large forces are required to get the torques to work. And that is the case of your back. So, when your mother says, lift with your legs, not with your back, she's actually a pretty sophisticated lady. She knew her biomechanics. Are there any questions on that example? Yes?
So just a quick one. When you have theta in the equations, which of the thetas are you referring to?
Well, these thetas are the same. That was that was sort of the magic of all that geometry, that business about this is perpendicular to this and this is perpendicular to this, made this angle the same as that angle.
I thought you were saying when that one got smaller, that would get bigger.
No,
I misunderstood.
If this angle gets small, so you're kind of like this, then this angle, which is with respect to the perpendicular, gets real small too. So that's the way I remember it, because I don't remember all those geometry rules. But I remember that one of these is theta, and that's the way I figure out which one, just from that little memory device. Other questions? Okay, so let's just talk a little more about biomechanics, and we'll have to be done for today. If you can do that problem, you can probably do any problem I throw at you on an exam for biomechanics. All right.
For like an example, do you already have the diagram drawn for us, or will you just give it to us like in a story problem?
I think I usually have drawn the diagram, but it would be fair to give you more of a story problem, but I'd have to really explain it rather in detail so there's no ambiguity. So I think on the past exams and practice exams, I usually give you the diagram. Let's talk a little bit about some of the implications of this. And the first thing I want to do is talk about when you ladies are pregnant, because pregnant women often have a pain in the back. So why is that? Well, here's the lady, and they have carrying a baby, but they're carrying their baby usually out like this. Okay? And so the baby has its own weight, and there's a fairly significant moment arm there. And that moment arm means the torques are large. And the torques are large, that means there's going to be forces on the back in order for the person to keep standing upright, because women don't want to walk around like this all day. So what you have is fairly large forces, and we won't work this out in detail, but there's fairly large forces on the base and the back because of the moment arm. Now, you can get rid of the moment arm if you can take the weight of that baby and distribute it around your whole waist, kind of symmetrical, like a weight belt. But you can't do that to a baby. So that's why the women are walking along like this, because they're trying to stop that moment arm. It's an example of biomechanics in action. It's exactly the moment arm issue that's the question. But the men don't get out of it, because the baby comes along, and now the guy's going to pick the baby up to play with it. Well, this is what you don't want to do. You don't want to be the guy, here's the baby. You don't want to be picking up like this for exactly the same reason we saw in the last problem. That's going to be an enormous, especially to hold the baby out because maybe the diaper is smelly or something. You can do this business, and you got a huge moment arm, about as big a moment arm as you can get, and that's going to be bad on your back. But if you have the baby in a snuggly, where you kind of got the snuggly, you know, you wouldn't be pregnant at that point. But if you carry the baby in a snuggly like this, and the snuggly kind of distributes those forces around the back of your shoulders and everything, you're spreading those forces out evenly, then you can kind of walk around not all day, it's still a little bit hard. You carry backpacks, it's kind of the same thing. But it wouldn't be so bad on you, and you could carry this around. So the snuggly keeps it real in close and kind of produces those moment arms. Okay, you know, it's kind of funny the way people are built, because people aren't built in the way that you might think would be the best way to build a person to lift big forces. For instance, suppose, first of all, how are people's arms built? If you're lifting things, kind of a curling motion. Okay? The way we do it is you have a big weight out here that you're trying to lift, and there's a biceps muscle. So it's pulling up like this. Well, this is a little distance, and this is a large distance out here to the end of your arm, and that's the whole problem. It's the difference in these moment arms is what causes this force to have to be so big. Wouldn't it make sense to make a wheelbarrow out of your arm, where you have your force out here, and the thing that you're lifting is in here? That, the design of a wheelbarrow, kind of works in backwards. Now, this force that you're lifting has the little moment arm, this force has the big, and you can balance everything out by just using a tiny little force here and to lift a great big force. So it's the principle of a lever. So our bodies are designed just the opposite of what you'd want to do to use the advantages of a lever. So let's imagine how we could redesign the body that we could make it able to lift great big forces. All right, so here's your person. We're going to redesign the body. So here's their arm. We want to be able to lift big things with the arm. So we don't want to be lifting way out here. We're going to stick their hand down here. And then we need to have the muscle, so it's going to be pulling up out here. Well, we can't just go up into Neverland, so we're going to have the muscle go up here, and it has to attach to something, so we're going to have a spine coming out of their head like this. All right? So now, here's the person. Here's the other arm, probably the same way. And now this person is going to be able to lift really big objects because now they got a short little moment arm here, great big moment arm here. It gets rid of all these problems. But it introduces other problems. First of all, this thing's going to get caught in stuff, and it's going to get all ripped up, and it's going to be a mess, and you can't wear your shirts properly. And also, one thing about these is even though it takes small forces to lift things, you wouldn't lift it very far because you don't get very much motion. So the total amount of work is really not going to be improved. But you'd be lifting small little distances, but you could lift great big forces. So really, when you're thinking about evolution, you got to wonder, this kind of looks ridiculous, but really, maybe it has some advantages too. You got to wonder why in the world you design things like that. Another thing is this would lift very slowly, even if you button your arm up fairly quickly, because this is in a shorter radius, you'd be moving things slowly. So if you want fast and you want large distances and you don't want stuff getting caught on other things, you do it like we normally built. But if you just want to lift big objects, you do it like a wheelbarrow and you have it built like that. Okay, just a little bit more here about some of the homework problems. Sometimes I'll give you a little tips about the homework problems just to kind of get you started. You can always, we'll have time during homework, right before the homework's due, to ask questions. Homework's due a week from today. So I would suggest you try to start these problems early so then you can come in and ask questions, especially next Wednesday, but even Monday we can have a little time. But just a few hints. Problem 1.16, that's in your homework. That is really the problem of doing curls. So really with these biomechanics problems, if you work out in the weight room, you'll see them because you live them every day when you're doing these. You're going to have your arm and you're going to have various muscles. You're going to have a weight out here, and you're going to have your biceps force, and you're even going to include the weight of the arm itself as a small force. So you're going to have four issues. The nice thing about this problem is that you're just holding the barbell. You're not lifting it yet. So it's a statics problem, and it's horizontal, so it becomes much easier. And all the forces are in the vertical direction. So this one ought to be easy to solve. But it's an example of doing curls. And then problem 17, another one. 1.7, excuse me, 1.17. 1.17. By the way, when I write the homework problems like this, it's chapter 1, problems 2, 6, 7, 16, 17, and so on. Problem 1 in chapter 1 is not in the assignment. There's 8 problems. Okay, problem 17 was another exercise. This is the lateral raise, but in our case, we're just going to be holding something out. But it's sort of the opposite of the rings. The rings, you were trying to avoid going like this because your muscles couldn't handle it. But the lateral raise, you got big weights out here, and you're trying to avoid going like this. So it's a different muscle. This was the pectoral muscle. This is the deltoid muscle in the shoulders that does the work. So what you have is your shoulder, and you have your deltoid muscle, and I call it T, and you have the weight. I don't know if it's the weight of an arm or a force. You have to read the problem. And you're going to have the shoulder exerting some opposite force. And again, it's horizontal, so it's not too hard. Those are the 2 problems that you're going to do. But some of these forces, some of the parameters, I didn't write down all the things, but these distances and angles and things are given in the problem, so you'll be able to work it. Now, if you want to, you can do additional problems. So one problem you might want to work on is, let me see where it is here in the book. Problem 8 is the Achilles heel problem. So imagine you're a diver, and you're standing on the edge of the diving board. So here's the diving board, and your toe is on here, and your foot's like this, and your foot is attached to your bone, and what brings it down and does and allows you to make this sort of motion is a muscle which is attached to the Achilles tendon. So we're really looking at the forces in the Achilles tendon, which will assume the same as in the muscle. That then you're just standing there, and the problem 1.8, which is not in the homework assignment, asks you to analyze the forces in the Achilles tendon. Again, they're very big because this is a small distance compared to this. The moment arms are so different. There was, it's been a while now, but one of the MSU basketball players, maybe 10 years ago, was a real superstar, going to become an NBA guy, and then he busted his Achilles tendon in some basketball game. And that's because these forces are gigantic in these tendons. They can experience really huge forces, and you can see why if you did that problem. Again, it's all the same issue, the same reason that you have these giant forces when you're doing the iron cross. Okay, the last problem, which I hope you'll read about and think about, is the problem of the cane. And the book goes into rather detail with that. I'm not going to redo it all in class. But the interesting thing about a cane, canes are to help you walk. And you use the cane, if my left hip is bad, I don't use the cane on the left side. You might think you use the cane on the left side, so it's like a crutch. But the purpose of the cane isn't so much to take up some of the weight off your leg. The purpose of the cane is because if you didn't have a cane and you were standing, so in the middle of the walking motion, you're kind of like this. In order to balance yourself, you kind of got this leg pushed over to the side, and you end up getting really large torques on your hip. And the cane would allow you to kind of stand like this, and the torques aren't quite so big. So you use the cane in the opposite side, and if you work that problem, you'll see that you actually have a very significant change on the forces on the hip because the cane was on the opposite side. So sometimes you get some interesting insights from this. Yes. That problem, well, it's discussed in the book, and then a variation of it is problem 11. But the problem itself is pretty much an example in the book that the book goes over in rather detail. So that problem is probably a little bit harder than some of the ones in your homework and some of the ones you probably see in the exam. It's not much harder, but it's just geometry is just hard enough that it might be a little bit much for an exam. But I do hope you'll look at it. Okay. Are there any questions? We don't have enough time to spend several classes on biomechanics. This is our class on sort of gross biomechanics, but we will be spending some more time in chapter 1 on fluid mechanics, which is the mechanics of how fluids flow. Fluid motion, fluid mechanics is one of those topics that is really important in biology, but you don't discuss much in introductory physics. It's almost always skipped because you don't have time in the introductory physics class. So we'll spend at least 2 classes on fluid motion, including Monday, when we'll be talking about stationary fluids or hydrostatics. And then Wednesday we'll go on to fluids in motion and discuss the fluid dynamics. And that's it. If you have questions, come up. But that is the class, and have a good weekend.